Welcome! Today, we'll tackle problem number 478, generate random point in a circle. This is an interesting challenge that combines geometry and randomization techniques. Let's dive into the problem and explore the different approaches to solve it. In this problem, you're tasked with designing a system that can generate random points within a circle. The circle is defined by a given radius and center, and the points must be uniformly distributed. This means that every area inside the circle has an equal probability of being selected. To achieve this, you'll need to implement the solution class. The constructor of this class takes three parameters: the radius of the circle and the x and y coordinates of the circle's center. Once the object is initialized, you will implement a method called randPoint. This method will return a random point, x, y, that lies inside the circle. The random point must satisfy the equation of a circle, which is x underscore center, caret 2 plus, y underscore center, caret 2 equals radius caret 2. Ensuring that the points are uniformly distributed within the circle is a critical part of the problem. Now, let's look at the input and output format in more detail. For the constructor, the input consists of three parameters: radius, which is a floating point number greater than 0 and up to 10,000, x underscore center, which is the x-coordinate of the circle's center, and y underscore center, which is the y-coordinate of the circle's center. Both the x and y coordinates can range from -10,000 to 10,000. The constructor does not return any output. For the randPoint method, there's no input required. The output is a list containing two floating point numbers, x, y, which represent a random point inside the circle. The point must satisfy the circle's equation, and every call to randPoint should generate a new random point that adheres to these conditions. To better understand how this works, let's go through some examples. In the first example, we initialize the circle with a radius of 1.0 and a center at 0.0, 0.0. When we call the randPoint method, it generates random points inside the circle. For instance, the output could include points like 0.5, 0.5, or 0.3, -0.8. The specific points will vary with each call since they are generated randomly, but they will always fall within the circle's boundary. In the second example, the circle has a radius of 2.5 and is centered at -3.0, 4.0. Here, the randPoint method might generate points such as -4.1, 5.2, or -2.5, 3.8. Again, the exact values will vary, but all points must satisfy the equation of the circle. These examples demonstrate how the method works for different circle sizes and centers. Finally, there are some constraints and edge cases to consider. First, the radius of the circle must be greater than 0 and no larger than 10,000. The x and y coordinates of the center must be within the range of -10,000 to 10,000. Additionally, the randPoint method can be called up to 30,000 times, so your solution needs to handle a large number of calls efficiently. Some edge cases include circles with very small radii, such as 0.001, where the points will be extremely close to the center, and circles with very large radii, such as 10,000, where the points can cover a wide area. You may also encounter circles that are not centered at the origin, such as one with a center at 5,000, -5,000. Lastly, precision is important to ensure the points are generated accurately and do not introduce rounding errors. These considerations will help ensure your solution is robust and handles all possible scenarios. To generate random points uniformly within a circle, we explored a few different approaches. The first is rejection sampling. Here, we generate random points within the bounding square of the circle by choosing x and y coordinates randomly within the range of the circle's diameter. Then, we check if the point lies inside the circle using the equation of a circle. If it satisfies the condition, we accept it; otherwise, we reject it and try again. This method is simple to implement and relies on basic geometry, but it can become inefficient, especially for small circles, because many points may fall outside the circle and get rejected. The time complexity per point is expected to be constant on average, but the variance can be significant depending on the rejection rate. Another approach is the polar coordinate transformation. This method involves working directly in polar coordinates. Instead of generating Cartesian coordinates, we sample a radius or by scaling the square root of a uniform random variable, which ensures uniform distribution across the circle's area. We then pick a random angle theta uniformly between 0 and 2 pi. These two values are converted into x and y Cartesian coordinates using trigonometric functions. This method guarantees uniformity, avoids wasting computation on rejected points, and is more efficient overall, though it requires some understanding of the relationship between polar and Cartesian coordinates. The polar coordinate transformation approach has a constant time complexity per point, as no points are rejected. Next, we considered a hybrid approach called grid sampling with rejection. Here, we divide the circle into smaller grid cells and pre-compute which cells are valid, meaning they overlap with the circle. During point generation, we randomly select grid cells and then generate points within those cells. If a point falls outside the circle, we apply rejection sampling, but within a much smaller area. This reduces the rejection overhead compared to the bounding square method. However, it introduces pre-processing time and is less efficient than polar coordinates for dynamic queries. The pre-processing complexity is quadratic, depending on the grid size, but the point generation remains constant time. Ultimately, we chose the polar coordinate transformation method. Its efficiency and simplicity make it the best choice for this problem. The breakthrough insight is that the area of a circle grows with the square of the radius, so to achieve uniform distribution, the radius must be scaled by the square root of a uniformly distributed random variable. This ensures that points are evenly distributed across the entire circle, both near the center and along the edges. Polar coordinate transformation stands out as the most efficient and accurate approach for this problem. Unlike rejection sampling, it avoids wasting resources on invalid points, guaranteeing 1 time complexity per point. By directly leveraging the circle's geometry, it ensures a truly uniform distribution of points without requiring additional pre-processing. Although polar coordinates may seem less intuitive at first, the actual implementation is straightforward and avoids the overhead of rejection or grid-based methods. When comparing this approach to rejection sampling, we see that while rejection sampling is easier to implement, its performance degrades significantly for smaller circles relative to their bounding squares due to high rejection rates. On the other hand, grid sampling can be effective when dealing with static circles and a large number of queries, but it introduces pre-processing time and added complexity, which may not justify its use in dynamic scenarios. In terms of overall complexity, the polar coordinate method achieves constant time and space per point, as it avoids additional data structures or pre-processing. This balance of efficiency, simplicity, and accuracy makes it the optimal solution for generating random points uniformly within any circle. To solve the problem of generating random points uniformly distributed within a given circle, we need an approach that ensures every point inside the circle has an equal chance of being selected. One effective method to achieve this is through rejection sampling. Here's how it works. We begin by defining the circle using its center coordinates, center_x, center_y, and its radius, r. Once the circle is defined, we establish a bounding square around it. The square's edges are determined by extending the radius outward from the center, resulting in x-coordinates ranging from center_x, r to center_x plus r, and y-coordinates from center_y, r to center_y plus r. This bounding square serves as the area from which we will generate candidate points for the circle. Once the bounding square is defined, the next step is to generate random points within it. We achieve this by randomly selecting an x-coordinate within the square's x range and a y-coordinate within its y range. These values are chosen using a uniform random number generator. After generating a random point, x, y, we check if it lies inside the circle. This is done by calculating the Euclidean distance squared between the point and the circle center, which is given by x center_x, ** 2 plus, y center_y, ** 2. If this distance squared is less than or equal to the radius squared, the point is valid and lies inside the circle. Otherwise, the point is rejected. This process is repeated until we generate a valid point. Once we find a point that satisfies the condition, we can output it as the result. The key advantage of this approach is that it guarantees uniform distribution within the circle. By generating points uniformly within the bounding square and rejecting those outside the circle, we avoid any clustering or bias in the distribution. However, the efficiency of this method depends on the ratio of the circle's area to the square's area. Since the area of the circle is pi r superscript 2 and the area of the square is 4 r superscript 2, the ratio simplifies to pi/4, which is approximately 0.785. This means that about 78.5% of the points generated in the square will be accepted, making the method relatively efficient. It's also important to consider edge cases. For very small circles, the random number generator must handle small ranges accurately. In the degenerate case where r equals 0, the circle reduces to a single point, and the only valid output is the circle center, center_x, center_y. To implement this algorithm, we rely on floating point variables to store the circle's parameters, such as its center and radius, as well as the generated coordinates of candidate points. Additionally, a random number generator is used to produce the uniform random values needed for point generation. In Python, the random.uniform function is well suited for this purpose. Let's analyze the key operations and their computational complexity. Generating a single random number is an O(1) operation, and so is the calculation of distance_squared, which involves basic arithmetic. The rejection loop, where we repeatedly generate points until a valid one is found, runs on average 1.27 times per valid point, as determined by the acceptance rate of pi/4. Therefore, the entire process is O(1) on average for generating a single random point inside the circle. There are also alternative methods and optimizations to consider. One such method is polar coordinate sampling, which avoids rejection altogether. This approach involves generating random polar coordinates, then converting them to Cartesian coordinates. While it eliminates rejections, it requires additional computations for the coordinate transformation. Another optimization is pre-computing the bounding square for fixed circles, which can save time in scenarios where the circle's parameters do not change. Finally, for circles within non-square bounding boxes, using a tighter bounding rectangle instead of a square can reduce the number of rejected points, improving the acceptance rate and overall efficiency of the algorithm. This implementation solves the problem of generating random points within a circle using the rejection sampling method. First, the __init__ function initializes the circle's radius and center coordinates, storing them as class variables. This allows the circle's properties to be reused across multiple calls to the randPoint method. The randPoint method begins by generating random offsets for x and y within the bounding square of the circle. The random.uniform function is used to create values within the range, radius, ensuring that the generated points are within the square that fully contains the circle. To ensure that a point lies inside the circle, the method calculates the squared distance from the point to the origin of the circle, using x_offset*** 2 plus y_offset*** 2. If the squared distance is less than or equal to the square of the radius, the point lies within the circle. This check ensures the uniform distribution of points within the circle. Once a valid point is found, it is translated back to the circle's actual center by adding the offsets to the circle's center coordinates, x_center and y_center. The method then returns the resulting point as a list of two coordinates. Rejection sampling is used here because it is simple to implement and guarantees uniform distribution within the circle. The efficiency of this method depends on the ratio of the circle's area to its bounding square's area. Since the circle occupies approximately 78.5% of the square, the rejection rate is low, making this approach computationally efficient for most practical cases. Here, we begin by importing the random class to help us generate random numbers. Then, we define a class called solution which will handle the logic for generating random points within a circle. This class has four private variables: radius, which stores the radius of the circle, x-center and y-center, which represent the coordinates of the circle's center, and random, which is an instance of the random class used for generating random numbers. The constructor of the class takes three parameters: the radius of the circle and the coordinates of its center. These parameters are then assigned to the respective class variables. Additionally, we initialize the random object here to ensure we have access to random number generation throughout the class. Moving on to the main method, randPoint, this function is designed to generate a random point within the circle. It continuously attempts to randomly generate x and y offsets within the square that bounds the circle, where both offsets are chosen from the range, radius. Once the random offsets are generated, we check if the point defined by these offsets lies inside the circle. To do this, we use the condition x offset squared plus y offset squared is less than or equal to the square of the radius, which is derived from the equation of a circle. If the condition is satisfied, the point is valid, and we translate it relative to the circle's center by adding x center and y center to the offsets. This ensures the random point is placed correctly within the circle centered at the specified coordinates. The translated point is then returned as a double array. If the condition is not satisfied, the loop continues, and new offsets are generated until a valid point is found. This ensures that every point returned by the function is uniformly distributed within the circle. Here, we start with a circle of radius 1 centered at the origin, 0, 0. First, the solution class is initialized with the given radius, x-coordinate, and y-coordinate values. These are stored as instance variables to define the circle. Next, we call the randPoint method to generate a random point inside this circle. The process begins by generating random offsets, x_offset and y_offset, within the square that bounds the circle. Since the circle has a radius of 1, the square spans from -1 to 1 along both axes. For example, we might generate x_offset equals -0.3 and y_offset equals 0.7. To determine if this point lies inside the circle, we use the condition x_offset ℏ2 plus y_offset ℏ2 equals radius ℏ2. Substituting the values, we calculate -0.3 ℏ2 plus 0.7 ℏ2 equals 0.09 plus 0.49 equals 0.58, which is less than 1, confirming that the point is valid. Finally, we translate this point back to the circle's center by adding the offsets to the center coordinates, resulting in the point -0.3, 0.7 as the output. Now, let's consider a circle with a radius of 2, centered at 1, 1. Again, the solution class is instantiated with the given parameters. The randPoint method starts by generating random offsets within the square bounding the circle. This square now spans from -2 to 2 in both directions relative to the circle's center, giving it a side length of 4. For instance, we might generate x_offset equals 1.5 and y_offset equals -1.8. To check if this point lies inside the circle, we compute 1.5 ℏ2 plus -1.8 ℏ2 equals 2.25 plus 3.24 equals 5.49. Since this is greater than the square of the radius, which is 4, the point is invalid. We repeat the random generation process until a valid point is found. For example, generating x_offset equals 0.8 and y_offset equals -1.6 gives 0.8 ℏ2 plus -1.6 ℏ2 equals 0.64 plus 2.56 equals 3.2, which is less than 4, so the point is valid. Translating this point back to the circle's center results in 1.8 minus 0.6, which is returned as the output. Next, we examine a circle with a radius of 3, centered at -2, -2. The solution class is initialized with these parameters, and the randPoint method begins generating random offsets within the square bounding the circle. This square has a side length of 6, spanning from -3 to 3 relative to the circle's center. For example, we might generate x_offset equals -2.5 and y_offset equals 1.2. To determine if this point lies inside the circle, we calculate -2.5 ℏ2 plus 1.2 ℏ2 equals 6.25 plus 1.44 equals 7.69. Since this is less than the square of the radius, which is 9, the point is valid. The next step is to translate the point back to the circle's center. Adding the offsets to the center coordinates gives -2 plus -2.5 -2 plus 1.2, resulting in the point -4.5 -0.8. This valid point is then returned as the output. Now, we consider a new example where the circle has a radius of 2 and is centered at 1, 1. These values are stored in the solution object as radius equals 2, x_center equals 1, and y_center equals 1. This defines the circle mathematically as all points satisfying x⁻² plus y⁻² less than or equal to 4, with the center now shifted to 1, 1. This setup ensures we can generate random points within the new circle's boundaries, which will be used for the next step. To generate a random point, we first define the bounding square for the circle, which spans from -2 to 2 in both the x and y directions relative to the origin. Suppose the first random point generated is -1.8, 1.5. Checking this point against the circle's condition, we calculate x superscript 2 plus y superscript 2 equals -1.8, superscript 2 plus 1.5, superscript 2 equals 5.49. Since 5.49 is greater than 4, the point lies outside the circle, so we discard it and try again. On the next attempt, we generate the point 1.2 minus 0.8. This time, x superscript 2 plus y superscript 2 equals 1.44 plus 0.64 is equal to 2.08, which is less than or equal to 4, meaning the point is inside the circle. Translating this point to the circle center, we add 1, 1 to 1.2 minus 0.8, resulting in the final translated point, 2.2, 0.2. This is the output for this example. In this example, the circle has a radius of 3 and is centered at -2, -3. The input values are stored in the solution object as radius equals 3, x underscore center equals -2, and y underscore center equals -3. The mathematical definition of this circle encompasses all points that satisfy x superscript 2 plus y superscript 2 less than or equal to 9, with the center placed at -2, -3. This new setup prepares us to generate random points within the boundaries defined by this circle. To find a random point, we start with the bounding square, which ranges from -3 to 3 in both directions relative to the origin. Suppose the first random point generated is -2.5, 1.0. Evaluating x superscript 2 plus y superscript 2, we calculate -2.5, superscript 2 plus 1.0 superscript 2 equals 7.25. Since 7.25 is greater than 9, the point is outside the circle, so we discard it and generate another point. This time, the random point is 0.5 minus 0.5. Checking this point, we find x superscript 2 plus y superscript 2 equals 0.5 superscript 2 plus minus 0.5 superscript 2 equals 0.5, which satisfies the condition x superscript 2 plus y superscript 2 less than or equal to 9. Thus, this point lies inside the circle. Translating it to the circle center, we add -2, -3, to 0.5, -0.5, resulting in the final translated point, -1.5, -3.5. This is the output for this example. To analyze the time complexity of the randpoint function, we start by looking at the steps involved. First, generating two random numbers, x and y, using random.uniform takes constant time, or O1, because it simply samples from a uniform distribution. Next, we check if the generated point lies within the circle by evaluating the condition x plus y equals radius. This calculation involves a few basic arithmetic operations, multiplications, addition, and a comparison, all of which are constant time operations, making this step also O1. Now, since we're using rejection sampling, the while loop will continue generating points until a valid one inside the circle is found. The acceptance probability is determined by the ratio of the area of the circle to the area of its bounding square, which is pi/4 or approximately 0.785. On average, the loop will execute 4/pi iterations to find a valid point. Since each iteration involves constant time operations, the overall average time complexity of the randpoint function remains O1. Now, let's discuss the space complexity of the solution. The solution class maintains three instance variables, radius, x underscore center, and y underscore center, which are used to define the circle. These variables require constant space, or O1. Inside the randpoint function, we use temporary variables x and y to store the coordinates of the randomly generated point, and the result is returned as a list. These temporary variables also require constant space, so their contribution is O1. Importantly, the algorithm doesn't utilize any additional data structures, recursion, or complex storage mechanisms that would consume extra memory. Therefore, the overall space complexity of the solution is O1, making it both memory efficient and straightforward. When comparing this approach to a brute force or naive method, the benefits become clear. A brute force solution might involve generating random points over a much larger area and filtering out those that don't fall within the circle. This approach would drastically reduce the acceptance probability, especially if the bounding square is much larger than the circle, leading to a significant number of wasted iterations and a much higher time complexity. In contrast, the current approach efficiently bounds the circle within the smallest possible square, minimizing wasted area. This ensures a relatively high acceptance probability of approximately pi/4, which helps keep the average number of iterations low. The use of rejection sampling guarantees uniformly distributed points within the circle without requiring extra computations or memory. In conclusion, this solution achieves optimal performance with an average time complexity of O(1) and a space complexity of O(1), striking an excellent balance between simplicity and efficiency to meet the problem's requirements. When generating random points inside a circle, there are a few common mistakes to watch out for. First, directly sampling a random radius uniformly between 0 and r, along with a random angle between 0 and 2 pi, may seem like an intuitive approach, but it leads to non-uniform point distribution. This happens because the area of concentric circles increases quadratically with the radius, meaning more points cluster near the center. To fix this, the radius should be sampled as the square root of a uniformly chosen random value. Another common issue arises in rejection sampling when bounds for x and y are set incorrectly. These must span the full square enclosing the circle, from r to r. If the bounds are too small, valid points are excluded. If they are too large, the algorithm becomes inefficient. Finally, floating point precision errors can occur, especially when dealing with very small or very large radii. This can lead to incorrect calculations or even infinite loops during rejection sampling, so it's crucial to account for precision limitations in your implementation. Another mistake to avoid is overcomplicating the conversion from polar to Cartesian coordinates. The transformation itself is straightforward: x equals or times the cosine of theta, and y equals or times the sine of theta. However, errors can occur if theta isn't sampled properly within the range of 0 to 2 pi, which is essential for uniformity. Additionally, rejection sampling can become inefficient in certain scenarios, particularly when working with small circles inside larger bounding squares. A significant portion of the sampled points may be rejected, wasting computational resources. In such cases, methods like the polar coordinate approach can be more efficient because they guarantee that every generated point will fall within the circle, avoiding unnecessary rejections. In interviews, it's important to recognize patterns involving uniform distribution problems. These often require transforming one type of random distribution into another, such as accounting for the nonlinear relationship between a circle's radius and its area. Be prepared for follow-up questions, such as justifying the uniformity of your solution or discussing the trade-offs between rejection sampling and the polar coordinate method. Interviewers might also ask about optimizing rejection sampling, such as pre-computing values or refining the bounds to reduce computational overhead. Extensions of this problem are also common, like generating points within a donut-shaped region between two radii or sampling from a hemisphere instead of a full circle. Familiarity with these variants can demonstrate your ability to generalize the solution efficiently. Related problems, such as random point generation in different shapes or using weighted random distributions, are worth reviewing as they often share similar concepts. There are several alternative approaches to generating random points in a circle, each with its own advantages and trade-offs. The polar coordinate method involves sampling theta uniformly between 0 and 2 pi and r as the square root of a uniformly chosen random value between 0 and r superscript 2. This approach is both simple and mathematically precise, ensuring uniformity, but it does require trigonometric calculations, which may be less efficient than basic arithmetic. Rejection sampling, on the other hand, samples x and y uniformly within a bounding square and rejects points that fall outside the circle. While this method is easy to implement and avoids trigonometry, its efficiency decreases as the circle-to-square area ratio shrinks, though it remains practical for most cases. Finally, inverse transform sampling uses the cumulative distribution function of the circle's area to directly generate points. While theoretically elegant and precise, this method is computationally intensive and rarely used in practice. Understanding these options allows you to choose the best approach for the specific requirements of a problem. Great job reaching the end of this problem. To recap, we discussed how to generate random points uniformly within a circle using polar coordinates. This approach highlights the power of mathematical transformations in problem solving. Thanks for watching, and we hope to see you tackle more coding challenges with us soon. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!